Okay, besides the functional dependencies, the closures, we can also calculate the closure of attributes actually, which is more important because based on the closure of attributes, we can check if certain attributes can be the super key or even a key or not. We can also check if some FDs can hold or not based on the existing attributes as well as the existing FDs. So what is the closure of a set of attributes? Generally given a relation as well as a set of attributes like A1 to AN. Based on a set of FD dependencies like S, the problem will be find all the attributes like B such that any relation which satisfies S also satisfies A1 to AN implies B. In other words, we want to find all the other attributes can be derived or can be implied from A1 to AN based on the existing FDs in set S, which will be the closure of A1 to AN, these attributes. So formally we can denote the closure of A1 to AN as A1 to AN with the plus added as a superscript, which covers all attributes can be derived, can be implied from A1 to AN based on the existing FDs. Why it is important? So by calculating the closure of some attributes, we can check if the attributes can be a super key or not. For example, if we want to check if the X equals to A1 to AN is a super key or not, we just need to check by computing the closure of X. We check the closure of X contains all the attributes in R or not. If so, then we can say the X can be a super key for the relation. Otherwise, we can say it's not a super key. What else usage? Besides the super key checking, we can also check if some FDs X implies Y holds or not. So by checking this FD, we just need to check if Y is contained in the closure of X or not. If so, in other words, based on X, we can imply Y with some FDs in our S set. Besides these two usages, we can also check if some attributes can be the key or not. How can we check it based on the closure of attributes? So we can check this based on the statement like this. Given a relation R, we want to check if some attributes like X equals to A1 to AN is a key of R or not. How can we check this? Based on the closure of attributes? I hope you still remember the definition of keys, right? Let me remind you again what is the definition of key. So given a relation, a set of attributes is defined as a key of a relation if and only if, first of all, this relation can functionally determine all the attributes of the relation, right? In addition, none of its subsets determines all the attributes of the relation. So based on definition of keys, we can say X is a key of the relation if and only if of R, if and only if the first condition is X is a super key of relation R, right? And none of the subset of X is a super key. Of the relation, right? We have two conditions. First of all, the X should be able to determine all the other attributes in the relation, right? And none of the subset of X can determine all the attributes of the relation, right? This is a definition we can derive. If we first use the closure of the attributes, how can we check if X is a key or not? We just need to check if X closure covers all attributes of R or not, right? And none of the subset x， none of the subset 那个e.g. 那个 y subset of x, right? And y closure, the closure of y can contain of R, right? So therefore, if we use the closure of attributes and we want to check if x can be the key or not, we just need to check if the closure of x can cover all the attributes or not of the relation R. If so, then we can say x is a super key, right? We also need to check none of its subsets, and the closure of this subset can contain all the attributes. In other words, none of its subset can be the super key, right? If so, then we can say x is a key of the relation. Therefore, by using this closure of attributes, we can also derive or we can also prove if some attributes can be the key or not for a relation. Then the question will be how to calculate, how to compute the closure of attributes. We have an algorithm prepared for you. Let me show the algorithm to go to the slides. So we have an algorithm as shown here to calculate the closure of the attributes. So given a bunch of attributes, like x equals to a1 to an, how can we calculate the closure of x? So we calculate the closure of x in a recursive way. So we repeat until x doesn't change anymore. And within the loop, in each step, so we check all the FDs in the S sets, like B1 to Bn implies C. And for each of the FD in the S set, we check if B1 to Bn are in the X or not. And we also check if C is in the X or not. If B1 to Bn is in the X set and C is not, if so, then we can add the C attribute to the X set. We do this in an iterative way until this X doesn't change anymore. And then we can return this X as the closure of the attributes. Right, this is the algorithm we can do to calculating the closure of the attributes. We will provide you with the example, and I can show you how to use this algorithm to calculate the closure of some attributes. Okay, so let's do the example together. And given the algorithm as shown here, we have the algorithm screenshot as shown here, and the question we have is shown as on our right hand side. Given a relation with multiple attributes, we have a bunch of FDs. A, B implies C, A, D implies E, B implies D, A, F implies B, and we want to calculate the closure of two attributes, A, B, as well as the closure of A, F, based on the algorithm as shown here. How can we do this? Maybe before I show you the answer, you can do the closure by yourself first on your paper.